Let's go ahead and get started. So it's my great honor and privilege to introduce our third keynote speaker, who is Surbhi Goel. Surbhi Goel is an early career faculty at UPenn, but she's already a celebrated faculty there. She's won a bunch of awards, and her work's been celebrated in many ways, most recently with one of the 2026 Computer Science Sloan Fellowships. So Surbhi's had a very interesting career. When she was a PhD student, she got very well known for a lot of very influential work at the intersection of computer science and statistics, or theoretical computer science statistics, a lot of computational hardness results, especially in the area of deep learning theory and related learning problems. And what's been very fascinating is that once she became faculty, she sort of blossomed in a bunch of directions, and she's basically a world expert now in everything which is adjacent to LLM theory and deep learning theory. So you can find many influential works on many topics from her. Of course, we saw 5 papers by her in yesterday's keynote. But also, I'll just mention one paper that gets a lot of attention. It's a beautiful work. It's called Shortcuts in Automata. It's one of my favorite deep learning or LM theory papers from the last few years. And actually, my favorite part's one of the ancillary parts of the paper. It's the log depth constructions in that paper. Just to close, I'll say one last thing about Surbhi as a person. She's also very dedicated to mentoring and advising roles. She already was a chair of assignments program. And also, we know from Monday, she's very involved with the Let All and many other advising and mentoring things. And she's one of my personal favorite people to talk to about not just technical topics. You'll see that she's just very easy to talk to on any technical topic, but also non-technical topics. So take it away.
That was an exceptionally kind introduction. Thank you so much, Matheus. It's a pleasure to talk to you about everything as well. And for just a note on the paper with the automata, that's like credit to all the other collaborators. There was a lot of collaborators on that, and it was like really a team effort. I can't take credit for it. And that construction was actually Cyril, so we should give Cyril the credit. Okay, so today I'm going to actually talk about reliable learning via abstention. So this is a line of work that I got interested during my postdoc. And it was a problem that stayed with me for a while. It took me a while to get some results in this direction. And then turned out my advisor was also thinking about these problems. And then some of the collaborators are his students now. So we ended up like now getting together and working on this. So this is going to be based on work before that. So I'm going to set the stage. Actually, luckily for me, we've already talked a lot about distribution shift. So I will have to hopefully not motivate this too much. And my clicker is not working. So give me 1 second. Okay. So one of the biggest challenges with current machine learning systems is that they don't often behave the way we want them to behave once we deploy them. And that's because the training and test time, there are a lot of different changes. So here are some examples that you guys might have seen before of like self-driving cars doing silly things when they collide with like stationary objects because they don't know what they're supposed to do in those situations, or medical systems where they make decisions on different patients that may not be appropriate because the training data is like somehow not calibrated to all the different populations that you might have downstream. One really fun example is this example. I don't know how many people saw this. This was this Apple Watch incident that the Apple Watch, whenever people were skiing, somehow thought that they were getting a heart attack and send 911. So this was another setting where maybe the training data did not really account for all the different behaviors that happened in test data. And some of these mistakes on this out of distribution or even sometimes adversarial data can be very costly. So we want systems that are somewhat reliable, and even if there is this kind of shift, we want them to behave really well in this shift. So what can we do? We've seen some different ideas already in the first session. So one of the ideas that people think about is like to restrict the shift in some way. So one thing that you could do is you could assume that there is some kind of relationship between test and train. So one thing is that there's a bounded density ratio, say like the probability mass that the test puts above the train is like bounded by some constant. So if we have that kind of a notion, then maybe we can hope for some transfer. If you're doing well in train, then we're going to transfer some of this performance to test. Another thing, we could have some other notion of distance between train and test. And if that distance between train and test is small, then we can have, again, some kind of transfer. So in some sense, these assumptions are necessary, as Shai and collaborators have shown. But for these guarantees to hold, measuring any of these assumptions can be very hard in practice. So we may not know whether in our test distribution is actually close to the train or the density ratio is bounded. These can be computationally very hard to verify. Now we can go to the complete other extreme, and we can assume the worst case. So we can go into the online learning model. We make no distribution assumptions at all. And we just think about learning as like every instance just comes to us, and we're making a decision. There is no distribution. And in that case, it's a great case. It's very robust. It can handle everything. But the learning complexity sort of depends on Littlestone dimension. And this is not great because Littlestone dimension is too pessimistic. Even for a simple class as linear thresholds in one dimension, this Littlestone dimension is infinite. So having guarantees in terms of Littlestone dimension is not very helpful. So in this talk, we're going to take a perspective of not trying to restrict the shift, but rather giving the learner an additional power of saying, I don't know. So the learner can have like some notion of uncertainty and decide, okay, I don't know how to predict on this instance. So here we will make no assumptions on tests. So a test can be anything. We might make assumptions on the training data, but we'll ask for two guarantees. So we'll ask for guarantees which are of this flavor, soundness. So what we want is that whenever the learner does predict, whenever it decides to predict, it should have low error. This is something we would desire from it. But alone, this is not enough because the learner can just decide to abstain on everything. So we would also want this other completeness guarantee where that the learner must predict on at least benign or clean data. So we want these two guarantees to be true. And I'll make these more precise when I talk about the exact models, what clean data means and what abstention error means. And so this, you can think of this as some kind of a proof system where your predictions come with certificates that whenever I do make a prediction, I have correctness. And this is kind of a nice property that you would want because now I can trust that whatever the distribution shift is, at least I'm getting a prediction that is guaranteed to be good. So this is, in some sense, selective classification, which is a very well-studied area, meets distribution shift. And I'm happy to take any questions in the middle, so feel free to interrupt me and raise your hands and ask me questions. So the talk is going to focus on this idea in two different settings. So we're going to first, in part one, focus on the batch setting. I'll talk about this really nice framework called PQ learning, which is by Goel, Kalai, and Montessor from 2022, which kind of abstracts this idea that I just mentioned about soundness and completeness. They don't say it in that way, but essentially the same idea. They already resolved the statistical picture, which I'll tell you. And then what I'm going to talk about is how can we make this computationally efficient in the batch setting. In the second part, we'll shift to the online setting. And here we'll design and define a framework where we will kind of extend this PQ learning framework to an online learning setting. And I'll describe this new framework that we came up with, and we'll show you some positive algorithms here that we can get very good rates, and we can get stochastic-like rates even in this setting without assuming any bound on how many adversarial injections there are. And here, this is going to be based on joint work with like some set of the authors that I mentioned before. I'll highlight them as we go. Okay, great. So let me start with the first part. This is joint work with Abhishek Shetty, Costas, and Arsen. They're all really great. Arsen is on the job market, and he's done really tremendous work in this area. So please look out for him. And the paper is titled Tolerant Algorithms for Learning with Arbitrary Covariate Shift. Okay, so let me set the stage now and make things more formal. So everybody knows the pack learning framework. We have training examples. We have X. And I'm going to assume for now it's realizable. Some of the results will go to agnostic settings, but let's just, for simplicity, assume that we have a true labeling function in our concept class. So we have training examples X and F star of X. And X is drawn from some distribution X. Think of this as like data from one hospital that we are training from. And in general, in pack learning, what we want is we want to output a classifier H, which has this following guarantee, that it gets low error. So if I sample more data from the same distribution, I should have low error on that data. So this is the standard pack learning. So what happens in PQ learning is the following. We have the same setting. We have the training examples from this trained distribution. But now we have test examples. So we get some unlabeled test examples from another distribution, which could be some other hospital here, for instance. And this is going to be arbitrary. We're going to make no assumptions on this test data. So it can come from anything, anywhere. We don't know what it is. We don't have labels, but we do have access to the inputs. And now we want to output a classifier H. And instead of just outputting a classifier H, we'll also output the selector G. And the selector is basically, you can think of a 0, 1 valued function, which decides whether I need to make a prediction or not make a prediction. Now the guarantee is the following, that when I decide that the selector selects the data point X, on this test distribution, the error that I have is bounded by epsilon. Okay, so this is the guarantee that I'm asking on the test distribution without making any test assumption on the test distribution, that whenever I do predict on the test distribution, my error is bounded by epsilon. The completeness is the following, that if I actually got data from my train, then I should not, the probability that I decide to not select that data should also be small. So in this case, we get like sort of both guarantees that if data looks like the training distribution, I am making a lot of predictions. And whenever I'm making a prediction on my test distribution, I'm getting low error. Yes.
So when you say look like it's only the marginal, you don't see labels, so you have to assume covariant shift.
Yeah. Good point. So F star is going to be the same through both. So it's a strong assumption. We're just, without that, we can't hope to do anything. We can go to the agnostic setting, then you get this parameter lambda, which is the minimum possible error between the two. And you can get these to extend to that setting. But right now, just assume that F star labels both test and train. To talk about epsilon error here. Good point. I should have mentioned that. Okay, so this is the setting. It's quite a nice model. It's not a priori clear whether we can get such guarantees without making any assumptions. One thing else to point out, there's another model which is called testable distribution shift. This is sort of the same model as PQ learning, but it is sort of easier in the sense that instead of asking for a selector, you can imagine the selector just decides that I'm not going to do anything on the entire test distribution. So it can just make a decision to reject the entire test distribution. So it's more like a decision problem versus here you're like, try to predict as much as possible on the test distribution. In the other case, if it's just slightly different, I can just decide not to do anything. We'll see some connections to that later. So that's the TDS model. So PQ and TDS, they're not the best names, but hopefully you're with me with this model. Okay, so cool. What's known? Of course, it's at least as hard as back learning, because if the test and train were the same, we would have to predict on everything. So we have to do at least as much as back learning. And it turns out this really nice result in this original paper that proposed this model, that the sample complexity of this model is actually exactly the same as the sample complexity for back learning. And it depends on VC dimension of F. So you can come up with a not efficient algorithm that basically runs ERM oracles a bunch of times to decide when to predict and when to not predict. Computationally, unfortunately, the picture is not so nice. That it turns out that it's actually equivalent to something known as reliable agnostic learning, which is sort of a one-sided agnostic learning guarantee. This is easier than agnostic learning, but it's harder than back learning. And it turns out that even for half spaces in D dimension, this is actually bad because you don't have polynomial guarantees, you have super polynomial rates, even for learning half spaces in this model. One thing that's nice is that when you do this reduction, you have to do, what you have to do is you have to keep changing the train distribution a bunch of times when you're calling the oracle. So this is like a distribution-free reduction. So we can still hope that we can get computationally efficient algorithms if we make some assumptions on only the training distribution. Yeah, question.
Yeah, the efficiency here is relative to the oracle, the Goel ERM answers?
No. So if you assume that, this is efficient because they reduce it to an ERM oracle. But the problem is that the ERM oracle is an agnostic ERM oracle, which we can't actually get up for even simple classes like half spaces. Yes. So as long as if you're happy with this fact that, okay, ERM is solvable, then yes, this result already tells you that you can run it a bunch of times and you can get this kind of guarantee. But if you're not happy with that, that maybe my ERM oracle doesn't produce anything useful, then you want to care about these computationally efficient algorithms that give you guarantees that ERM would actually work. Great. Any other questions? Yes.
How does epsilon depend on the mismatch in these results? The amount of abstentions were bounded by epsilon, right? So wouldn't it depend on the amount of shift, the number of abstentions, and how does it depend?
So very good question. So the whole model actually does not really have the TV distance guarantee. So let me just go back to the setup here. So what you're asking for is on the test distribution, I'm not doing condition on this. I'm doing, when I do decide to make a prediction, my error is bounded. And this is not actually, this is the error on the test distribution. Here, this is on the train distribution. So I'm not saying that I'm going to abstain less on the train distribution. If my train distribution, test distribution is very far from my train distribution, I could abstain on everything. So if I wanted to transfer this to the test, I would get the TV distance. So this is kind of a nice model that kind of puts away the TV distance. We don't have to worry about it because the guarantees are very reasonable, that you should not expect to do better than this, because if your test was completely arbitrary, did not even have the same support you could hope to do. But at least you can try to make sure that you're not abstaining on things that look nice or that you should have been able to predict. Cool, very good question. Okay, so let me go back. So I'm going to try to motivate you that we can actually get efficient algorithms, and for very general techniques, we can like kind of transfer things that we know in the agnostic learning setting to in like the computationally efficient agnostic learning setting to these PQ learning settings, which are like much stronger guarantees because your predictions are now reliable. Okay, so let me give you an example to motivate you the challenge here. So we'll think of this class of half spaces. We'll assume that P, the test distribution, sorry, I'm calling it PQ. I should have called it test and trait. So the train distribution is Gaussian. So we made this assumption that the train distribution is very well behaved. Test is arbitrary. And we assume there is some half space that actually separates our data. We're going to look at two cases. It'll become clear why these cases. So the first case is that the actual bias term in my ground truth is very small. It's like bounded by 1 over epsilon. And the other case is the bias term is very large. Okay, what happens in these two cases? So in the first case, if the bias is small, if I draw samples from a Gaussian, okay, this was supposed to look like green and this was supposed to look like red, but at least you can see the differences. So when I draw from a Gaussian, because my bias term is not very large, I'm going to see positive and negative examples, right? So I'm going to get some information about what the true half space is here. So this is a setting where training data is useful. What happens when the bias is really large? So if the bias is really large, the Gaussian is like centered around the origin. If the bias is very large, what's going to happen to, what am I going to see? Very few, I'm going to either see all positives or all negatives. I'm very unlikely to see both sides. So what can happen is that I could end up with like all these negatives and I don't know where the half space is. So this is completely uninformative. And if I want to make predictions here, I have to be careful. I cannot, I need to not, because the test distribution could put all its mass here or its mass on the top or the other side, but I don't know where my W star is. So I don't get much information from my training data, which is why somehow, deciding what parts to eliminate is very important, like where I should not make predictions because I'm not sure. Okay, so let's look at what happens in case one. Case one turns out that if this is the case, there are efficient algorithms, not efficient in epsilon, but efficient in dimension that you can get such that you can actually recover the true half space within very close parameters. If this is true, just believe me that there's efficient algorithms to do this. Once I have this, what can I do? So I have a W star, I have some W that's very close to my true W star. What can I do? So I know that this prediction is going to be good in areas that are far away from my half space, because there my predictions are going to be right because W star and W hat are going to be very close to each other. But near the decision boundary, I don't really know. So what I could do is that I could decide to create this disagreement region. This is a very common notion where I have two hypotheses that sort of disagree on the label. And I can decide to abstain everywhere in this region. The nice part is that for the Gaussian distribution, if this bias is small, this disagreement region can't be very large. So on the true Gaussian distribution, I'm not going to abstain too much. So this is great. This is pretty common in different kinds of methods in active learning and other things to look at this disagreement region. But this is not enough, because if I was in this case, I would like abstain on everything that was outside because it could be anywhere, the W star. So disagreement is not enough. But let's just assume that we can do this prediction. Okay, if you've seen only negative examples, predicting negative is a good idea, right? So we want to predict negative. Now we want to decide where all we should predict negative. So how do we get this predictor function? One thing to notice, just by a Markov inequality, is that the misclassification probability, when am I going to be wrong? When W star dot X will actually be greater than 1 over epsilon, which is my threshold. So if I'm like really far out is when I'm going to be wrong. And this is bounded by what my variance in that direction is. So if I can control the variance of my data in that direction, then I can make sure my error is small. And how do I control my variance? I basically look at directions. If I see a direction that tells me on my test data that the variance is really large, I just remove points that make this variance large. And I keep repeating this process till I like cut out, like I find this direction V. I remove all points such that my dot product with that direction is very large. I cut this out. Then I repeat the process again till I have no such direction left. And once I have no such direction left, my error will be bounded because I would be able to control this quantity. And so this turns out to be like basically cutting out like different half spaces and getting an intersection of half space. And now I know that my prediction is always going to be right because there's no direction that can witness any kind of error. And since Gaussian variance is bounded, we cannot remove too many examples from the original distribution when we are doing this, because we're choosing the threshold such that not too much mass can be of a Gaussian in that space. So we'll still maintain that we're not abstaining on the original distribution much. Okay, so this is a toy example and doesn't get you the best bounds, but this idea, the spectral outlier removal, actually generalizes very well. So what we can show is that instead of doing just this quadratic polynomial that I showed you, which was just the variance, we can take this more generally to any polynomial of some degree. And what we can do is the same process that we look for a polynomial that has very large moments or large variance in my data, and I remove examples that make this variance large. Because my distribution, if my training distribution is well behaved, it shouldn't have such polynomials. And once I remove this region, I can get these error guarantees that I had previously. So this is a lot to parse, but we come up with a spectral outlier algorithm that gives us this guarantee. And basically it says that the filter data will preserve polynomial expectations, and these expectations will look like how they are in the trained distribution. And we won't remove too much of the good data. Couple of things, there's been a lot of work on outlier removal. So something that's very interesting about this outlier removal algorithm is that it does not care about how many corruptions are there. So most outlier removal algorithms require like you're only bounded eta amount of corruptions, which is less than half. Here you could have everything be corrupted as well. That's okay.
But you still assume that the train is a normal distribution.
Yes. So we actually don't need it to be Gaussian. You can handle anything that has bounded moments. Like basically you want that this polynomial is well behaved on the train distribution so that we can have this process makes sense. So Gaussian, I think log concave and these kind of distributions work. We also don't really have efficient algorithms for a lot of general distributions and agnostic settings. So we're trying to transfer those at least to the setting. Yeah.
To do this, the selector tree depends on the sample from the test distribution, right? It's allowed to do this in general. It doesn't need to be said once for depending on the train example from the test distribution.
Right. So we need to use the test because we are trying to see where the test is violating this high moment. So it's going to be adapted to the test. That's why it's in the transductor setting. If we didn't have the test, any unlabeled samples, then this would be hard to do. So it is tuned to the test distribution. If I get a different test distribution, I might get a different boundary of selection. So I need to really use this transductivity of to get this thing to work. But the good point that turns out interestingly here is that it doesn't care about how many, it never uses how many samples are corrupted. So everything is corrupted, we'll just eliminate most things. Because the guarantee only you want is that you don't abstain too much on the train distribution. And the other nice thing is that these constants that we get do not depend on the degree of the polynomial. Only the runtime depends on the degree of the polynomial. So we can take the degree that depends on epsilon while not paying anything in this constant. So this was like kind of the technical part that let us get this result. So once we apply the spectral outlier removal, we can remove parts of the distribution that do not behave really well. But we also have to argue why removing polynomial parts are actually helpful, right? Why removing this helps. So it turns out we can show this very general result that if the concept class has this sandwiching polynomial, which I will explain in a second, it's like an idea of how well a function class is approximated by polynomials. If you have that with some degree k, then you can get an algorithm that runs in time d to the order k poly 1 over epsilon for the strain distribution, Gaussian, and like a bunch of other distributions. And the sandwiching polynomial is a very strong property, but turns out to exist for a lot of classes. It's this following property. It's a lot stronger than just approximating by a polynomial. You're asking for something really strong. You're saying that the function itself is upper bounded and lower bounded by a polynomial. Always. And the guarantee is that on the train distribution, the upper polynomial and the lower polynomial are very close. Yeah, so this is a very strong property that I'm asking, that everywhere there is a polynomial that upper bounds and lower bounds. Now the upper bound and lower bound could be really large. All I care about is that on the train, this distance is small. So you could have like arbitrary large values, but as long as on the Gaussian, this is well behaved, it's fine. So this is harder than approximation because you can approximate, there are classes which you can approximate really well, but sandwiching polynomials are hard to construct, or you need to pay a lot of higher degree. But as long as this exists, we can do it. And why is the intuitive idea? I'm not going to go through the proof, but the whole outlier removal was trying to deal with only polynomials. So now that f star is kind of upper and lower bounded by a polynomial, I can just replace f star by these polynomials cleverly and apply my outlier removal. So the error that would be between f star and any of these polynomials can be transferred into error between two polynomials, which is bounded now because I've removed all the points where the p square was different. And turns out the spectral outlier removal outside of this PQ learning has a lot of really cool applications. So there's this problem of learning with contamination or nasty noise, where an adversary can come in and remove a fraction of the data points and change them to something else. You can get algorithms that work in that noise model by using this outlier removal. And follow-up work by my collaborators and a bunch of other people have actually used this and strengthened the spectral outlier to handle, like, instead of the p square, like an absolute value of p. And this has led to new results which solve like long-standing open problems. So for example, you can learn AC0 circuits with nasty noise by using this kind of spectral outlier removal. So it's a really powerful technique. It also, I don't know how many people have heard of testable learning before? If you raise your hands. Okay, a few of you. So testable learning is also another way of, like, you can think of this abstention as giving us testable properties for distribution shift. Testable learning asks for, we make all these assumptions that our algorithm works if the input distribution is Gaussian, but we can't test whether our input distribution actually is Gaussian. So if we get a solution, how do we know it's actually good? So testable learning adds a test, which helps you check whether your assumptions are actually true. And it's a really cool line of work, which kind of motivates this abstention as a way of a test. So our algorithms also allow you to get some tolerance so that, even if there are small TV shifts, we don't reject because our tests can still pass. And we do this for TDS learning as well. So these are just some applications of this general spectral outlier removal algorithm. Okay, so any questions on this before I shift to the online learning setting? Yeah.
Do we need some sort of lower bound on the number of test examples that we get for this work?
Yeah, so okay, very good question. I actually need quite a lot of them. So if you see the outlier removal algorithm, which I conveniently hid here, the size of the training set that I need is pretty large, because I kind of need to check these polynomials, how they're behaving in the test. I need them to concentrate. So I need enough samples to make sure that I'm getting good estimates. So this is really in the regime where I have like test and train about the same size.
What is K here?
K is the degree of the polynomial. So if my degree becomes like really bad function of epsilon, I'm like paying a lot of samples. Yeah, so this is true. Like I can't, like, it would be great if I could do with like a few test samples decide, but I think I need to really have surety of what the moments are on that test distribution. And for that, I need a lot of samples. Yeah, question in the back.
What's the
Yeah, so okay. So here it's poly in 1 over epsilon. But what happens is that what I need to do if I want to get guarantees for, like, say, half spaces or any function class, my degree that I need to approximate with depends on epsilon. So k becomes a function of epsilon. So then I get d to the k. So I get like, so for half spaces, I get log 1 over epsilon. So I get d to the log 1 over epsilon. Even though this part, this outlier removal, if degree is constant, is polynomial in 1 over epsilon. But otherwise, I would have to pay a heavy cost. Yeah, so there are SQ lower bounds that say that these are almost tight. So yeah, you can't hope to do better because you're asking for a very strong guarantee to be like robust to everything in the test. And you want to make a lot of predictions. So you have to kind of know the certainty. Yeah, so we can't improve that. But I think the sandwiching trick, I don't know if it's necessary. Whether we need sandwiching, we could maybe do it with approximation itself or some other technique. We kind of have an idea that approximation is not enough, but sandwiching is perhaps too strong. So you could hope that you can improve these results. So it'd be interesting to understand like what is the right notion of how much surety do you need for this function class to actually get such guarantees. So we don't know that. Yeah. Yeah.
Do you have any algorithms for the case where D trained is just some Gaussian rather than like, or maybe like, yeah, you just know it's a Gaussian?
Yeah, so okay, so in the testable learning setting, this is called like universal learning. So you assume that the test distribution is some Gaussian or some log concave. Distribution could be any log concave, so they can get some guarantees that work. In our model, we haven't been able to yet. But there could be hope for something more universal. So like assume that the train is from like this class of distributions, then can you hope to get? So this would be like a universal PQ learning, which does not assume a particular train. Yeah, we could hope for that. I think not me, but my collaborators have like developed a lot of techniques that I hope they will eventually solve this problem beyond just like this first outlier removal technique. Okay, great. So let me go ahead. Yeah, so this batch setting is nice in the sense that I have this clean training data, and then I have arbitrary test data, and then abstention helps with this to get computational tractability. But usually this is also a strong assumption that your training data is completely clean. So your training data could also be corrupted. And decisions might not be like, oh, which was asked, like if I have this huge test data set, I can decide where to predict or not. But what if I don't have an entire test data set, right? So I want to make a decision at every time step, whether I should make a prediction or not. And this is more, in recommender systems or chat bots or a medical diagnosis. I'm making a decision per chat or per person. I'm not making like or collecting all this distribution and then making a decision. So what happens in that setting? So that motivated me during my postdoc to think about this question of like how to extend this model to online learning. And we did come up with this nice model, which I'll describe now, which is kind of somewhere between, it'll be very familiar now once you've seen PQ learning, why we chose this model, but it took us a while to come up with like the right model where we could hope for some guarantees. So let me describe it to you. So just to remind everybody what online learning is. So here we are, instead of getting like a training data set and a test data set, we're getting training data one at a time. So you get X1, X2, so on till XT. Your algorithm makes a prediction, and then you see the true label. Then you get to update your algorithm, and you can keep going ahead. And the kind of guarantee that you hope to get is now, instead of getting error, you kind of hope for regret, which is like the total number of mistakes that you made by the algorithm are somewhat bounded. And as t goes to infinity, the average number of mistakes goes to 0. So you want some rates that are like little o of t, so that you can like, the total number of mistakes doesn't grow as much as t. It grows slower than t, so that you can hope to get something nice. Okay, here also I'm going to make this assumption that there is a fixed label function, f star, that is labeling everything. I don't know how to extend this to general noise settings yet. Okay, so one regime you can assume is like the stochastic online learning, where you assume that there is a data distribution, and x1, x2 are just IID draws from your data distribution. This is a very benign setting. You're just assuming you're taking the batch setting, but just putting it online. And if that is true, then you can get regret that depends on VC dimension of the function class. And this is the notion for offline learning. So online learning reduces to that. The other extreme you can take is like fully adversarial, that each time there's an adversary which knows exactly what algorithm you're implementing, what has gone in the history, and decides what next example to give you. And here you can't do much better than little stone dimension, which I already mentioned, can be infinite even for a class that has VC dimension 1. So this is like very extreme. So the model that we think about here is the following. We assume there is a clean distribution. Let's call this like some nice distribution D, which the learner does not know, has no access to. Maybe in some cases we'll show we need some access to get anything interesting. And what happens is now the adversary at any time can decide, before seeing the IID draw, decide that this is the round I decide to corrupt. So I'm going to send my example instead of the example that would have come from the IID point. Okay, so it can decide whenever it wants, how many times the adversary wants, it can decide that. But very important that it does not see the stochastic input before doing this. Because otherwise, it's very hard to know what the IID distribution is. We still want, if we remove the adversary, everything else is IID. Okay, so this doesn't help you at all, because if the adversary decided to inject every round, you're back to the fully agnostic setting. So there again, you go to little stone. So we will use our power of abstention. So what we'll say is that we will allow the learner to not always have to predict. So they can decide to abstain on some instances. And so they get this extra option apart from predicting +1, -1, which I changed to 0, 1 here by mistake. They can decide to abstain. Okay, so what kind of guarantees do you want? Again, I'll go with this soundness and completeness that I said. So I want the misclassifications to be low. And I also want that the algorithm should not abstain too much on IID examples. When actually the round was not corrupted, it should not be able to abstain too much. Okay, so you get these two kinds of errors. The first one is that on the rounds that I decided not to abstain, my error is small. And this is the rounds that were not corrupted and I abstain, this is also small. The nice thing here is that abstentions on adversarial examples are free. So if you abstain on an adversarial example, you don't pay any cost. Think of this as like, oh, you have some, you detect that this example is something that you don't know, you go to a proxy or you get like some other label or whatever else you run in your machine. For like self-driving car, you give it to the human to control. Which is why we can actually get a guarantee that this error does not need to scale with the number of injections. Because if your learner can like adapt to this, the learner does not actually pay a cost that is proportional to the number of injections. If they can like decide to abstain on all the injections or make good predictions, that's also fine. They don't have to like actually identify which one's a bad point or not. They just need to know whether they can be certain about this prediction or not. Okay, so there's like a bunch of connections too. I'll just go through this quickly. If people have looked at this, there's like this really nice model called Know What It Knows. And there's also been work on like using abstention to get fast rates. Most of these settings are like fully adversarial or purely stochastic. Here we're kind of trying to mix the two and use this for distribution or like having some adversary in the middle of a clean stream. There's also, you can think of this as like a model of beyond worst case, because here now there's like a true distribution and a fully adversarial setting and you're somewhere in the middle. And there's been a lot of interesting work on doing beyond worst case study using a smooth adversary or like assuming your sequences are predictable or you have some hints about what the future will look like. So this is another way of this. And there's also a lot of work on adversarially robust learning, where if you have test time attacks, what can you do? If you have training time attacks, what can you do? So there's been a lot of work in this space as well. For our setting, sort of, if you notice the model, we can have our, up to the point that we're making a prediction, our stream can be corrupted itself, and the test point can be corrupted as well. So we need to handle both. And one thing that I forgot to mention, maybe it's important, is that the learner never gets to know which data was actually clean. So the learner does not have information of like, oh, it cannot just look back and be like, oh, this were all the clean points, let me just look at them. The learner does not get that information. They just get the label. So here kind of you want to deal with like test time and training time attacks together. So it'll seem like this is not possible to do, but let me try to motivate you something like this is possible. So let's go back to this simple example of linear thresholds. This is the class that has VC1, but little stone infinite. And we'll see that this abstention actually gives you a lot of power here. So what is this class? It's a very simple class. You have a threshold A. If your value is larger than that, you predict positive. If it's less than that, you predict negative. Okay, so what the adversary can do is choose a random A. Okay, the colors are not that great, but these are the negative examples and these are the positive examples. Say so far it saw some examples. The learner saw some examples, so it knows that this region, at least, it's seen some example at this boundary and some example here. So this one negative example and one positive example. So it knows that because it's realizable, everything here should be positive and everything here should be negative. But the learner does not know what's going to happen here in the middle. So what can the adversary do? The adversary can give you a point in the middle. So the adversary can inject a point here. And now if the learner had to predict, the learner does not really know what is happening here. So it's going to have like half a chance of getting this right or wrong. So if the learner must predict, it'll make mistakes on this with probability half and leading to this T/2 error. But what can you do? If you're allowed to abstain, I could just abstain on this entire region. I could just be like, oh no, I don't know anything. I'm not going to make any prediction here. What happens to our errors? What happens to misclassification? We are never making a prediction when we're not sure. So misclassification is trivially 0. Now what happens to incorrect abstentions? So let's think about this. If we have seen T-1 IID examples, what is the probability that the new IID examples actually falls between this and this point? Is actually going to go down very quickly, because it has to be between 2 points that were IID themselves, and this is 1 over T, because there are these many intervals that I have. So the new point being there is going to be 1 over T. So this is just a simple exchangeability argument that the ID points don't have any order in between them. So if I could have like seen the reverse order and I could have seen like that point before. So it's only 1 over T chance that a new point will fall between exactly this region. And if you sum this up, it just comes out to 2 log T. So you get actually log T abstentions. So realizable case. Everything is realizable. I don't know how to do non-realizable yet. Okay, so this is a great technique, which is also reminds you of the first example that I showed where you can construct this disagreement region and you're done, but you're not done because you can get 0 misclassifications, but the incorrect abstentions actually depend on the star number of a function class, which is very well studied. But star number is actually infinite for most classes. So even though I said, okay, little stone is, okay, I get down to star number, but star number is also not great. So this is not the end of the story. And you should notice that like I did this trivial thing where I just made the misclassification error 0, but I should be able to use somehow this misclassification error. So let's look at this other example of intervals. Okay, this is a class where star number is actually infinite. So now instead of like having 1 threshold, you have 2 thresholds, A and B. And now you want to make a decision. So imagine that this happened, this was true, that, oh, now I can see the red really well. Okay, cool. The IID distribution had the true distribution put very little mass on positive points. Again, very similar to the batch setting. So all you saw was negatives. If you did this disagreement strategy, what would happen? Because you don't know where the interval is, every point is in the disagreement region. So you would have abstained on everything, which is not great because your IID distribution is basically negative, so you should have predicted negative. So this is not going to be good. So it's better if I just predicted negative everywhere. What would happen if I did that? If I predicted negative everywhere, I wouldn't have a misclassification. Error would not be 0 because there could be a positive example somewhere and I could see it. And so we need to be careful about this error. And let's see what happens. Okay, so if the learner decides to predict negative everywhere, say I get a point here. And if my algorithm actually made a mistake, what would happen? I would get a positive label. Now what that helps me is that once I know that this label is positive, what is the problem reduced to? Now it's just 2 intervals, two thresholds, just in one in this direction and one in the other direction. So I can go back to the other algorithm that I showed you before. So by making one mistake, I sort of reduced it to a problem where now I can abstain on the disagreement region and solve this problem. And then again, what will happen is that I will get these 2 log T sort of abstentions after this step. And I paid 1 misclassification error. So this is sort of saying that I want to continue making predictions such that if I did make a mistake, I would learn a lot at least. So I cannot keep doing this forever. So there's this like nice trade-off between the 2 errors. And that actually motivates our algorithm. But we kind of need this. Here I give you this toy idea that, okay, predict negative is the right strategy. You need to have some notion of uncertainty of like your function class at that point to decide when to make a prediction or not. And No. So I'll give you an algorithm for like general VC classes, but it's going to be very strong. It's going to assume that I know the marginal so I can compute these quantities. Without that, intersection close is a good intuition. I don't know how to do intersection close, but I can do like thresholds and axis aligned rectangles and certain classes like that. VC1 I can do and things, but yeah, it's not clear what the right class structure you need. But if I knew say I had access to the marginals of the true distribution, not the labels, I could do something good. So there's this idea of, if you know VC dimension, you know shattering. Shattering basically tells you like how much uncertainty you have in your class right now. So you could define this notion of shattering at different levels. So what does that mean? Is that I could look at drawing like k points from my distribution and seeing if these points are shattered or not. Like how likely are they to be shattered? And this gives me some uncertainty at like which level of complexity I am at. So if you think of the interval that has VC dimension 2, I made a mistake and I came down to 2 problems of VC1. So I kind of like went down this hierarchy, and I'm going to use this shattering as an idea of estimating which level I'm at. And if you think about this a little bit more carefully, so ρ1 turns out to be the first level is just the density of the disagreement region. So when you go down to level 1, you're just in that strategy, like disagreement region is small. If you're high up, it is a non-increasing function. And if you think about it, rho d plus 1 is going to be 0 because no d plus 1 points can be shattered because the function class itself has VC dimension d. So this is a nice kind of potential that you can play around with to know how uncertain you are about your points right now. And so the algorithm turns out to be like a kind of a halving algorithm. So what you do is you start with your current level, which is k equal to d. To make a prediction on on a new point that you get, what you do is you compute this function, thinking that if the label was positive or negative, what would happen to this quantity? How much information would I get from this if I got this label at this point? So I get these two quantities. If both are large, we'll abstain because I'm not getting much information from these labels. Else we predict with the larger one, whichever one is larger. And if both quantities are small, we already know everything about this level. We just go down one level and we do this algorithm. And once you're at level 1, then you can go back to that strategy of like abstain always in the disagreement region, otherwise make a prediction. So this is basically the algorithm. This is like the technical condition of when you decide whether to abstain or not. Okay, so one thing that's nice is that you cannot make too many mistakes because you're reducing every time you make a mistake. You are making sure that one of these two things were bounded, was large. So you go down to the smaller space, and you can only do this so many times because eventually you're going to go down to the level 1. So this is bounded. This is kind of like the halving idea that each time you're reducing your number of function classes. For IID points, the nice thing is that because I'm using these quantities, if you think about it, if my point was IID and both these quantities was large, what would happen? That I'm saying that if I add this IID point, I can actually create a k plus 1 sized shattered set because the fact that both these quantities are large, with this label being 1 or label being 0, I can find k other points that are shattered, and I can combine them together. This cannot happen for IID points that often because I was already, when I went down, I already guaranteed that my top level was lower, small value. So this cannot happen too much for IID points. So we can show, it's a little bit, it's actually just a Markov inequality applied a little smartly, but it basically shows that if these both quantities are large, then this gives us a witness for the value above it being large, which is not possible by our algorithm. So IID points cannot abstain too much. So this gives us this kind of a guarantee where misclassifications are bounded by d squared log t and incorrect abstentions are bounded by d. And this sort of d squared d is kind of suboptimal. Somebody I know knows how to fix this d squared to d log d, but they have not written it up. So that's why I haven't put the citation there, but hopefully they'll write it someday. They went into finance and are coming back to academia, so I hope they will write this down. Yeah, but you can get it to d log d, so that it's like kind of balanced. And also works if the adversary doesn't fix this f star, but it keeps like make sure realizability holds, but can keep adaptively changing its f star if it wants to change it as it goes along. The sad part is, of course, this requires like marginal access to the distribution to compute this shattering. Computing shattering is going to be really hard because you're trying to see at level D, if I take D points, whether they're shattered or not. And if I wanted to do this with samples, this would require a lot of samples. So this is not a very efficient algorithm. And checking shattering can also be very computationally inefficient. So of course, you can ask this question that what happens if we don't have access to this marginals? Now I cannot run this algorithm, but I could hopefully do that. So since I don't have that much time, I will just basically tell you that that setting becomes a little bit more tricky. First, we can show a lower bound that for a VC1 class, you have to pay square root t. So you don't get this nice log t kind of guarantees that you got before. So already, if you don't have access to the distribution, you are suffering more error. This is unavoidable. But we can get algorithms that get this kind of rate. And just as an intuition why, maybe this is a fault of the design of this model. But basically, if you don't know, you kind of have to make sure that you're not making incorrect abstentions on the IID examples, but you don't know where the IID examples are or what the IID examples are if you've never seen any examples before. So the adversary can kind of hide can choose like, can divide your time into like the square root t sort of chunks and choose one of them to be IID. And then there's no way for you to figure out which one's IID. So you have to decide between either abstaining or making misclassification. So in either case, you get some kind of error. So this is sort of like the problem. If I have no idea what my base distribution is, how do I know which one was my base distribution? And the adversary showed me very similar looking distributions. So square root t is sort of there. But we can get this. So we can get for some concept classes. So VC1, we can get using Shai's tree sort of construction. We can get like a potential function that is sort of like, we can't get the shattering probabilities for general classes, but we can get some potential that gives us this algorithm that if that potential is large, we can, it cannot be large for IID examples too often, so that we can make sure that even if the adversary adds anything, it cannot be very large. And so we can get some progress on that. It would be great if I had more time, I could explain the algorithm, but it's like some idea of making a potential that's more robust in the same way like of shattering, but like something more sophisticated using the geometric structure of the problem. We can get it for rectangles. We can get it for inference dimension. This is this nice notion in active learning with queries. Even though we don't have query access, we can use this idea to get an algorithm for every inference dimension k. We can get it for half spaces. And the VC1 basically matches the lower bound because the lower bound was square root t. We get a upper bound of square root t, so that's tight. Half spaces, we come up with a new notion of a generalization of this dimension. If I'd given this talk on Monday, I would say this is an open problem to do this more generally. But literally on Monday, somebody put a paper on arXiv, which is Moish and his student put out this paper that they came up with. They kind of took that shattering idea and made it implementable without access to the distribution under an oblivious adversary. So the adversary is oblivious. It cannot be adaptive to the learner. Then they can actually implement that algorithm using some boosting technique. And it's a really nice paper that I haven't gotten a chance to digest properly, but they're able to get this t to the 3/4 rate for all VC dimension classes, assuming that the adversary is oblivious. These all are for like adaptive adversaries. So they're incomparable in some sense. But this is a cool, decent progress as of Monday that you can do things with t to the 3/4 rate. So you can implement that shattering thing without paying so much as sample complexity. Okay, so just to summarize, I guess the key message of this talk is abstention can enable certified predictions. And in settings where standard learning can be intractable or impossible, just adding this extra feature of abstaining can be very helpful to get guarantees. You can obviously criticize that, what do we do once we abstain? We're like pushing the problem to somebody else, but at least our predictions somewhat mean what we're asking them to mean, and that's the best we can hope for here. So I think this is a cool idea. Like if we can get our predictions with this certificates, they're more useful in practice. There's a lot of open questions. So in the batch setting, we only do it for like some structured distributions like Gaussian or these moments. You can ask for like more general distributions that are more faithful, like mixture of Gaussians or things like that. Even more generally, like what are the conditions that you need on the input distribution that gives you this guarantee. For online, we actually don't have the right notion of complexity. So we don't know what is it VC dimension or is it some other notion of complexity that governs this learning? These are like some, we came up with this certificate dimension, and that paper, the new paper comes up with this reduction dimension. These are all some new notions, but we don't know which one actually characterizes learning. So it's an open problem. What is the right dimension for this? Again, all the online stuff is with like labels being realizable. There's this really nice, it's actually a master's thesis by a student who's now, Carolyn, who's now a PhD student at Copenhagen, who got interested in this paper and tried to generalize to random classification noise. And it turns out even for the simple class of linear thresholds, this becomes challenging, because once you have noise, you don't know which thing to trust. Even if your labels you're getting, they're noisy. So you have to be careful about how you maintain your which part to abstain, which part to not. So she got some results for that, but this is quite open of what you can do, or whether you can't do anything. That's also possible. And then beyond binary classification, you could go to like multi-class, partial concept class regression. The nice thing is this doesn't rely on uniform convergence, because we were using this shattering kind of arguments. So you can hope to like generalize to a lot of these different classes. And then this thing I'm really interested in, and we're working on something with imitation learning, but like beyond supervised learning, we have distribution shift everywhere in more interactive settings. So can we get like some guarantees of reliability in like more interactive settings like imitation learning or RL, where like we say we are in like, we train our model in some like synthetics or like some setting which is very well controlled and want to deploy it in the real world. Can we get this kind of abstention guarantee in more interactive models? So this is also like, there's a lot of things that we could try here by adding this abstention in various different problems. And that's all I got. Thank you for listening. Happy to take any other questions.
We have time for a few questions.
Learning with abstention feels a little similar to learning partial hypothesis classes. I wonder if there's like insight from that has been drawn to this or could potentially be.
Yeah, I think it is true, but like I think so that's why I kind of mentioned it here, that hopefully there's like some extension of this, but I don't really know how to use partial concept class directly for this abstention problem, because the kind of guarantees we want is a little bit different, right? So yeah, it would be great. I should spend more time reading that literature, so I haven't done that. But yeah, it doesn't seem like there's a direct map that I could use just for partial concept class, but it'd be great if there is some reduction like that.
Is there reduction for conformal prediction? Because the conformal prediction, we have VOC here,
yeah,
which is the big expert of conformal prediction, but it looks related.
Yeah, that would, so yeah, it would be great if there was a very direct reduction. So there's this other model that you could imagine where you change the costs to be like not just additive, like bounding both errors, but adding like a cost to abstention. And I think there's a paper by Varun Kanade and Silva Kasabura. I'm going to mess up her last name, but they try to connect this to conformal in the setting where there's like a trade-off between the two errors. So yeah, it'd be great like if there are like connections to these other areas, even sort of like, the whole entire robustness literature is also probably like connected in the more broader sense, because all the techniques we're relying on is like trying to figure out where our predictions are not accurate. And so any kind of robustness technique would also be helpful here. So yeah, it'd be great to see if there are these connections.
I have one question. So it seemed like a lot of the methods, in both parts. The first part was maybe a little easier for me to understand. So you would learn both the underlying predictor and the selector G at the same time.
Mm-hmm.
I was wondering if you guys have thought about settings where you're handed a predictor and then you just have to choose a good selector, maybe to be able to boost the prediction in good areas. If it's a calibrated predictor, of course, we can use the calibration, but if it's just like a classifier. So I was wondering if you had comments on this.
Yeah, that's a good question. So in some settings, actually, what we need is just like an ERM to start with. If as long as it's an ERM, we can like get these regions out. So I guess it's not entirely true. Like in the first setting, what we do is we come up with like a polynomial approximator. We just like run that, and then we only eliminate areas. So we're not actually changing that predictor. We just decide where to use that prediction. But generally, co-designing them makes it a lot easier because this is a polynomial, I can control what is happening. But yeah, it's a good question. Like if I was just given something, can I decide? And then I think I would have to have the rate depend on like what kind of classifier it is or some property of it, because I won't be able to control, what property should I look at for this classifier. So the general reduction actually just requires an ERM though. So maybe ERM is enough. But that's a good question. It would be great if I could just like, in an LLM case, I just get this model, I just make a decision when I should predict or not predict. But I guess calibration is probably more useful there. When, yeah.
You mentioned the connection to
Yeah. I think it's that in that setting, you just get like, you can predict everywhere and you can still get VC-like guarantees. So it's smooth just makes it easier, a lot easier to do. Here, it's like the adversary can like hide points in like, that's the challenge. Like if the adversary puts it in the disagreement region at some level, we can't really make a prediction. If it's smooth, the adversary cannot do this so easily. So yeah, we thought initially that there would be like some interesting area where smooth and abstention makes sense, but maybe you can like improve the smoothness dependence. But I think straight up, like you can always predict who would smooth adversaries. You don't have to abstain. I don't think you get much from abstaining.
But I guess for smoothness, you still need samples from the base distribution or something like that. I forget.
Yeah, I don't know what the latest work on this is like, but I thought it was like generalized quite a bit. But yeah, maybe you need some base distribution access because at least the original algorithms were to construct like some covering and then do some kind of algorithm on that. But I think there are like other reductions where you can just use ERM by this. There's a more recent paper that does that. So I don't know off the top of my head, but yeah, it could be. There could be something interesting. But in our settings, we tried like wherever we put smoothing, we didn't need abstention. It just like worked. So we didn't get anything interesting from both. But yeah, could be interesting to see.
It would be interesting if combining both, you could get rid of the requirement for sample basis.
Yeah, that's possible.
There's maybe one last question.
I'm curious about what you think about the imitation learning or RL setting. Are you thinking about like adversarial injection of these training environments? Or?
Yeah, so the problem, I can tell you what we are trying to work on right now. So in imitation learning, it's kind of like supervised learning in some sense because you're trying to imitate the expert. So what you can imagine is like, let's look at the batch setting. What happens is you train a model with an expert policy in your environment, simulated environment. Say it's like a self-driving car, you know exactly what the actions it took because you had all this, a human was driving it, you saw the actions. And then you have YouTube videos of like the car being driven outside. Now you don't have the actions there and the transitions are different. So there's been a distribution shift, not in the sense of like now the environment is completely different. So can we make some guarantee that, we abstain whenever this transition is too far out so that we don't like incur costs, like in a driving case that if the roads are slippery, I should not make a decision at that point. I should just abstain at that point in my trajectory and then stop. So we're trying to like model like what we can get in that kind of setting and how it depends on how long the policy is running and things like that. But yeah, I don't know the RL analog because RL, you're like choosing your data as well. So what is the distribution shift that I should think about, or like what is the right setting? I haven't thought so much about it. So I just started with imitation because it's closest to supervised learning.
Thanks a lot.